Hey everybody, welcome back. Today we are going to be taking a look at acids and bases lesson 4, which is indicators. For today's review, we are going to be doing two problems. The first is determine the pH of 3.82 grams of nitric acid being dissolved in 920 milliliters of water. So we are looking for the pH of 3.82 grams of nitric acid. So when we are involved with a problem like this that gives us grams and we need to find the pH, first we need something to relate to the flow chart. And the way that we find out what relates is by doing step 1, writing a balanced ionization or dissociation reaction. Because this is an acid, we are going to be doing a dissociation, an ionization reaction. All right, so nitric acid looks like this, HNO3 aqueous will ionize to form H plus and NO3 minus. Great, from here you're going to list what you know and what you are looking for. So the only thing that relates to our pH flow chart is this right here, our H plus content, okay? So this becomes our unknown. We have 3.82 grams of nitric acid. So 3.82 grams of nitric acid. We are going to find the concentration of this H plus because it's the one that'll relate to the flow chart. Molar concentration, we're going to relate that with our volume, 0.920 liters. Great. Since we are looking at grams here, we're going to have to convert this into moles. And the only converter that we can use for this is our molar mass. Our molar mass for this guy is 63.01 grams per mole. Let's go on to step 2. Step 2 is find H plus. If we find H plus, we have hydronium concentration. Okay, so I'm going to go ahead and start with what we know. So this is our known. Start with this. 3.82 grams of nitric acid. We need to convert this into moles using our converter molar mass, 63.01 grams per mole. Okay, now we are going to convert this. Okay, so I'm going to use my converter. Grams cancels out with grams, and here I'm going to use my molar ratio to convert into moles of my unknown. I have 1 mole, because ones are invisible in chemistry, 1 mole of HNO3. Okay, so HNO3 cancels out with HNO3. And then there is 1 mole of H plus. Okay, mole cancels out with moles, and I have moles of my unknown. The last thing I need to do, I am looking for concentration, moles per liter. So I need to divide these moles by our volume. So I'm going to take this, divide it by 0.920 liters. Okay, let's go ahead and plug that in. 3.82 divided by 63.01 times by 1 divided by 1. Don't need to put the step in. but some of you get very uncomfortable if you don't do it. Won't hurt to do it, won't hurt to leave it out. Then divide by our volume, 0.920. I get a concentration of H plus, which we know is equal to H3 hydronium concentration, 0.6, sorry, there should be a 0 there. 0.0658 ... moles per liter. So I'm just going to leave that answer in my calculator for now. The last step is find pH, and we're going to use our flow chart. So I've been given my hydronium concentration, and I can convert that into pH. So I'm going to go negative log. I'm going to take my concentration, 0.0658, ... and that's going to give me my pH. So in my calculator, I'm going to go negative log of this answer, close the bracket, enter. And I get a pH of 1.18. Okay, going back up our significant digits, the lowest number that I see here, I have 3 significant digits and 3 significant digits there. So I actually need to include one more digit, 1. My final answer is pH is equal to 1.181. Awesome. Okay, moving on. The second review question says, for each of the following scenarios, identify if pH will increase or decrease. So if we're adding water to a basic solution, we know that water is neutral. So if you're adding water in a basic solution, it's going to actually approach neutral. So that's going to decrease our pH. If you're adding water to an acidic solution, again, you are going to be approaching neutral. So you are going to increase your pH. Okay, so just to visualize this, let's say we have an acid sitting here in the acidic region and we add water. It's going to approach neutral. Therefore, the pH increases. Same thing, here we have our basic region. If we add water, it's going to approach neutral because water usually has a pH of 7. So it's going to decrease our pH. The last question, hydronium ions increase. If hydronium ions increase, that means it's going to become more acidic. If it becomes more acidic, it's going to lie in this acidic region here. Therefore, pH decreases. So today's learning goals are going to be differentiating between monoprotic and polyprotic indicators and estimate the approximate pH or pOH range of a compound using indicators. All right, so for indicators. Indicators are used to determine the pH of an unknown substance. So a lot of times, a lot of laboratories, they are given soil samples, water samples, and they need to determine the approximate pH range of it. So an unknown substance using a qualitative. Qualitative means that you're looking at the physical appearance of the solution. Does it form a color change? So we're going to do a qualitative analysis in the form of color change. So we're actually going to be looking at what the colors are when we put the indicators in. In a chemical reaction, acids lose a hydrogen ion, and bases gain hydrogen ions. Indicators are weak acids and bases. Weak acids and bases, that should say that, will change color in response to a solution. Okay, so we're going to be talking about indicators now. In your data booklet on page 10, you will see all of the listed indicators, okay? You're going to notice that there's a couple of columns here. We're going to be using the first three columns. The indicator, I'm just going to talk briefly about the abbreviations, but we will be using the indicator column and the pH column most likely. So some indicators have one hydrogen. Therefore, they're only capable of one color change. So if we take a look at methyl orange, and methyl orange is fifth down in the indicator column, we'll notice that it exists in two forms. H, M, lowercase o, and when it is this state, it is red, okay? Or if it loses that hydrogen and becomes MO negative, that is a horrible M, let's try that again. MO negative, then it will be yellow. Okay? So here's how this works, how we're going to use it to narrow it down. If the pH was below 1.4, then the unknown would turn the indicator red. Okay, so if it's below 1.4, it would turn the indicator red. And I'm looking at these numbers in the pH range column. Sorry, I can't write on the data booklet, but I'm leaving it there so you guys can see where I'm grabbing the information from. Sorry, this is not 1.4. Okay, it is actually going to be 3.2. So if it's below 3.2, then the unknown would turn red. If the pH is between 3.2 and 4.4, then the unknown would take an in-between color, so kind of like an orangey, orange yellow, orange red, depending on which side it's closer to. If the pH is above 4.4, then it's going to take on a color of yellow. Okay, so we're kind of understanding what that means. We'll notice that other indicators are polyprotic. That just means that it has multiple hydrogens. And that means that they can have multiple color changes. For example, thymol blue is a very common indicator. And if it has H2TB, it's going to be red. Okay. If it loses one hydrogen, it becomes HTB minus, it's going to be yellow. And lastly, if it loses both of its hydrogens, becomes Tb2 minus, it's going to be blue. Okay? Now, if the pH is below 1.2, then the unknown would turn the indicator red. If the pH is between 2.8 and 8, it would turn the indicator yellow. And lastly, if the pH is above 8, then it would turn the indicator blue. Okay, lovely. Let's do some indicator problems now. When you are given an indicator problem, you'll either get a data set on a table, or you'll be in the lab actually physically seeing the color changes happen yourself. So once you have your data, you're going to go into your data booklet and turn to page 10. The first unknown says, use the following data to determine if the pH of the unknown. Lovely. So what we're going to do, the first indicator that they've given to me is methyl orange. Methyl orange turned red. So if we look at methyl orange, it's the fifth one down, and read across, the pH range is 3.2 and 4.4. If it is red, it is going to be below, it's going to be below 3.2. So it's going to be less than 3.2. Okay, from here, I recommend that we draw a pH scale. Okay, so 0, 14, 7. So now on this pH scale, I'm going to locate 3.2. It doesn't need to be exact, but I'm going to say, okay, 3.2, probably somewhere there. And the pH range is 3.2 or less. So I'm going to draw an arrow that way. The next one we're going to pick, we have bromo-cresol green. I look down, it is right under methyl orange, and its range is 3.8 to 5.4. And it turned it yellow. Actually, my apologies. This should not say bromo-cresol green. It should be saying thymol blue. Just gonna change that. So this should be thymol blue. And yes, it did turn it yellow. So I find thymol blue. It's the third one down in the indicator table, and it has two ranges. It's a polyprotic. It goes from 1.2 to 2.8, 2.8 to 8.0, and then 8.0 to 9.6. So if it's turning yellow, that happens between the range of 2.8 to 8.0. So I'm going to now go 2.8 to about 8.0. Now this one, I'm actually going to enclose the box. Now, from here, you're going to see where they overlap, where both of the indicators overlap, which is happening right here. So your pH range is equal to 2.8.3.2. Now the thing with indicators is you can't really get an exact pH, you'll get a range. Okay, so this would be my final answer, 2.8 to 3.2. We can't say where it is directly between there, so I have to report the whole range. Okay, the next example, use the following data to determine the pH of the unknown. So again, we're putting two indicators into it. First thing that we're going to do is draw my scale. Okay, lovely. From there, we are then going to look at our indicators. So the first one turned bromothymol blue. It turned it blue when we put it in there. So that means if we find bromothymol blue, the range is 6.0 to 7.6. Let's grab a different color here. That means it's going to be a pH greater than 7.6. Oh boy. Okay, so I'm going to find 7.6. and it's going to be greater than 7.6. The next one is phenolphthalein, and phenolphthalein turns this vibrant pink color with strong bases. But in this case, it is colorless. So we find phenolphthalein, the range is 8.2 to 10.0, and it was colorless. So it's going to be less than 8.2. Okay, so I'm going to find 8.2, and I'm going to go that way. Okay, then we see where they all overlap. It overlaps right here. pH is between 7.6 and 8.2. Lovely. Okay, example 3, use the following data to determine the pH of hydronium, pH and hydronium concentration of the unknown. Okay, so from here we now have 3 indicators that we're using. Same situation. I'm going to first start off with our pH scale. 0, 14, 7. Okay, phenolphthalein. Phenolphthalein turned colorless, so that's the same. It's going to be less than 8.2. So I'm going to find 8.2, and it's going to be less than. The next one is bromothiamyl blue, turned blue. Bromothiamyl blue, I'm going to find that to turn blue, so it's going to be 7.6. And it's going to be greater than 7.6. The last one is phenol red. Phenol red has a range of 6.6 to 8.0, and phenol red turned red. So phenol red turned red. That means it is going to be greater than 8. So 8 is right in between these two. Now I'm going to find out where all 3 indicators overlap. And that is going to be this region right here. So pH is equal to 8.0 to 8.2. Okay, there's 1. Now it's also asking us for hydronium concentration. So you're going to go ahead and get your calculator out and then calculate your hydronium concentration. So H3O plus is equal to 10 to the power of negative 8, which gives me 1.0 times 10 to the negative 8 moles per liter. H3O plus is equal to 10 to the power of negative 8.2, which gives me 6.3 times 10 to the negative 9 moles per liter. Just good rule of thumb, when you are listing mathematically, you always list smallest number to biggest number. So our hydronium concentration range is going to be 6.3 times 10 to the negative 9 moles per liter to 1.0 times 10 to the negative 8 moles per liter. There is our hydronium concentration, and here is our pH. Okay, time for you guys to try one on your own. When you are ready to check your answer, you can unpause the screen. Okay, so this is what I get. I then fill it in where everything overlaps. So pH is equal to 1.0 to 1.2. All right, last little section here is selecting an indicator. You are trying to determine the pH of an unknown substance. Which indicator would you start with, bromothiamyl blue or phenolphthalein? Take a moment here to put in your answer, hypothesize, and when you're ready, you can unpause. So when selecting an indicator, you want to determine if you are working with an acid or a base. The first thing you want to do is determine if it's an acid or a base. Therefore, an indicator like bromothymol blue, makes sense. If the pH is below 7, then the unknown will be an acid. If the pH is above 7, then it will be a base. So it doesn't really make sense for us to waste our indicators. You want to get right off the bat narrowing. So we want to determine if we're working with an acid or a base, and then we can pick other indicators to turn it down. So now, for example, the unknown turns the indicator bromothymol blue, blue. Therefore, indicating that this is a base. Okay, so if bromothymol turns blue, that means it has a pH of 7.6 or greater, therefore in the basic region. Then, what would our next indicator be? What indicator would it make sense next? Methyl orange or phenolphthalein? So let's take a look at methyl orange. Methyl orange is testing 3.2 to 4.4. It's testing an acidic region. Phenolphthalein is testing between 8.2 and 10. It's testing a basic region. So since we are working with a base, it makes sense for us to choose phenolphthalein as our next indicator.